So let us consider some applications of the Fourier transforms. But before we get there, let me just clear up one or two important results that I will be using a little later on, so we don't have to pause when we come to those results. Just remember the following facts that we have learned earlier in the course. If you take a first order differential equation of the type, let's say, w double dash plus lambda w equals to 0. Oh, sorry, that's a second order differential equation. I meant to say, let's take a first order differential equation. Let's take w dash plus p of w equals to q. So this first order differential equation can be solved by the integrating factor method. So if you multiply throughout by the integrating factor, which is e to the integral of p, then you'll get a case of w dash e to the integral of p plus p e to the integral of p w equals to q e to the integral of p. In other words, here you get d dx, let's say x, e to the integral of p w equals to q e to the integral of p, etc., etc. So to get w by itself, you integrate this once. That's e to the integral of p w equals to integral of q e to the integral of p. So w is given by e to the power minus integral of p, integral of q e to the integral of p. In that way, you can get that explicitly. So that's one thing. The second thing that I'll need later on in the applications is how do you solve second order differential equations of the type, let's take w double dash plus lambda w equals to naught. Now this has got three possible options. Either the w is equal to a cos something plus b sine something, and this is when the lambda is more than 0, or it's ax plus b in the case when lambda equal to 0, or it's a cosh something plus b sine something when the lambda is negative. The lambda here, notice, is a negative, is an eigenvalue. So when the eigenvalue is negative, in this case the coefficient of w is negative, so then you will have cosh and sinh. So we will need this a little later on in the game. Something else which I will use later on is find the Fourier transform of a function f of x equals to, say, x over x squared plus 1. I'll use this as an example later on. So this is going to give us something called f of k. And so in order to find this f of k, that's 2 over pi integral of x e to the minus I kx dx over x squared. Well, actually, this is we are going to actually find the Fourier sine transform. So let's focus only on that. Fourier sine transform, so it will be x sine kx, and at the bottom we'll have x squared plus 1 dx. So effectively, we are going to find that Fourier transform from naught to infinity. So in order to achieve that, that's a bit difficult to achieve. So we can probably convert this to, by using the principal value and so on, to 1 over pi integral from minus infinity to plus infinity x e to the I kx over x squared plus 1 dx. Now this is actually an even function. Well, this is even for sure. This one here we don't know. It has cosine and sine in it, and we want just the imaginary part of this result at the end. So let's just deal with it as it is, and at the end we'll hit that with the imaginary to get the final result. So I want to apply the residue theorem. That's why I went to minus infinity to plus infinity. In that case, I'll have to find the poles The poles will be obtained by z squared plus 1 equal to 0. Z equals plus or minus I. Standard technique, plot I minus I, throw a contour around that, that's semicircular, and so we only need the value at the I itself. So we can say that the f of k is 1 over pi 2 pi I, the residue of x or z e to the I kz over z squared plus 1 at the point z equals I. That's applying the residue theorem. And let's crank this out. It's 1 over pi. It's 2 pi I. To work out the residue here, we can apply the idea of taking the numerator as it is, ikz, dividing it by the derivative of the denominator, which is 2z. And then we substitute z equals I, of course, in that. So that's, of course, we can cancel that. So that's 2I. Of course, we can cancel the 2 as well. So it's just I. And then this substitution here, the z's cancel off as well. Is e to the minus k. I squared is minus 1, so it's minus k. And the actual answer is the imaginary part of this. So the imaginary part is actually f of k, the sign, and that's e to the minus k. And this is valid for k less than 0. So by using complex conjugation, we can consider the case of k more than 0. Because remember, in the proof of this result, we made use of Jordan's lemma. It only works when k is less than 0 in this particular problem. So for k more than 0, we apply the idea that f of k is the conjugate of f of minus k. Conjugate of f of minus k will be e to the k. And the conjugate of e to the k is still e to the k. So we can say that f of k may be summarized as e to the minus absolute k. That covers all, for all k. Fine, so we'll use this a little later on in the game. Now, let me talk about the derivatives of, rather transforms of derivatives. Transforms of derivatives, some of them, not all. So, in the applications, we're going to be dealing with the heat equation. You may recall that it has a shape ut minus alpha uxx equal to, say, some function of x. It could be 0, but in this case, we'll take f of x. You'll see why that is important later on. The wave equation, or Laplace's equation, if you like, has got uxx plus uyy equals to naught. Now, let's try to find the Fourier transform for ut. Fourier sine transform of ut. So that's 2 over pi integral ut sine k pi x kx dx. And since we are doing dx, this can be written as d dt of 2 over pi integral u sine kx dx. And that's precisely dt of u, actually. So we call this capital U, in other words, capital U t, where this capital UT has got the same behavior for the Fourier integral theorem. Here, uxt can be written as the integral from naught to infinity of some u of k sine kx dk, where this capital U is defined to be 2 over pi integral naught to infinity u sine kx dx. That's Fourier's integral theorem. Fourier integral theorem. So this integral that you see here, this integral here, is precisely this integral here, which is capital U. So small u is a function we want to find, but capital U will be the Fourier transform. All right, let's proceed further. Let's try to find the Fourier transform for uyy. In the same way, you will find the Fourier transform for uyy. That's 2 over pi integral 0 to infinity uyy sine kx dx. Effectively, it becomes a squared dy squared of 2 over pi integral u sine kx dx, because we are dealing with dx here, and so u is a function of has got y in it, so the derivative can be pulled out of the integral. In other words, this is precisely capital U y y. Right? We won't be so fortunate with the next one. How about Fourier transform of uxx? This is 2 over pi integral 0 to infinity uxx sine kx dx. Now this time you can't pull it out because it's got an x in it, so therefore it can't be pulled in front of the integral sign. So we have to hit this with integration by parts. So if we apply integration by parts, we can say let u equals to, well, let's not use u. So we can use f and g. So we'll use the fact that it's fg minus integral, so it's uv minus integral v du. So it'll be integral of g df, fg minus integral g df. So f, let's put f to be sine kx. So df will be k cos kx dx. And let's put df to be uxx dx. Integrating this once, you'll get f to be ux, just one derivative. So this will be fg minus integral g df. That's the integration by parts procedure. That's 2 over pi fg will be sine kx times, so this should have been d, that was f, this is dg. This is the df is equal to k cos kx, so this here would be g. This would be g. So we misuse the letters here. This is dg. Let dg be equal to that, so g works out to be ux. So it's fg minus integral g df, integral g df. So fg will be ux sine kx. The limits are from 0 to infinity, minus integral g df. So it's k ux cos kx dx, 0 to infinity. Now you should be able to see that this is going to be 0. The derivative at infinity should be 0 because in a rod at infinity there can be no exchange of heat. You can't lose any heat beyond infinity, so that should be 0, and sine 0 is 0. So therefore this boils down as minus 2k over pi integral of ux cos kx dx from 0 to infinity. Now let's give this another round of integration by parts. This time we shall take let f be equal to cos kx. So the df is equal to minus sine kx, minus k sine kx, minus k sine kx dx, and that's dg be equal to ux dx. And if you integrate this once, you get g equals to just u. So this becomes minus 2 over k pi, and this is fg minus integral g df. Fg will be u cos kx, not to infinity, minus integral g df. So this will be a plus effectively. It will become k u sine kx dx, not to infinity. And again, you should realize that this is going to be 0. U at infinity is taken to be a finite number. It's going to be considered to be 0. And likewise, u at 0 is 0 for the rod that we are going to be considering. Therefore, this effectively boils down to minus k squared into 2 over pi integral u sine kx dx from 0 to infinity. And if you were observing closely, you'll find that this is minus k squared capital U. This guy is precisely the same as U, this entire thing. So then the Fourier transform of uxx is minus k squared U. Just to summarize that, what we have achieved so far is that Fourier transform of small ut is big ut. Fourier transform of uyy is big uyy. And the Fourier transform of uxx is minus k squared u. So this will now be useful in our understanding of the heat equation and so on. Let's now take a problem with the heat equation, and we'll solve this by the direct transform method. Direct transform method. Those transforms that we just achieved now will be used to calculate the profiles of the heat function. So the heat equation, let's say it's ut minus alpha uxx equals to some function of x. Let's say u at infinity is 0. U of 0 is also 0. And at time equal to 0, let's say we have a rod of this type here. It's infinite length. Okay. And so the initial condition, let's say initially the temperature is also 0. U of x 0 is 0. Now we can solve this problem by using the methods that we learned in the first semester. In other words, using separability and so on. But now we want to achieve this in a much more compact way using the techniques that we have. So if you take equation 1, let's hit that with the Fourier transform. Take the Fourier sine transform of equation 1 on both sides. The Fourier sine transform of ut minus alpha Fourier sine transform of uxx equals to the Fourier transform, sine transform of f of x. This is capital ut. Here it's minus alpha, and remember this was minus k squared capital U. Fourier transform of f of x, we'll call it f of k, capital F of k. All right, so just to simplify that a little bit, ut plus alpha k squared U equals to f of k. Now we can hit this with, this is a first order differential equation. We have the integrating factor, as explained in the first part of the lecture, e to the integral of alpha k squared dt. That will be e to the alpha k squared t. We multiply throughout by that, we will end up getting d dt of e to the alpha k squared t u equals e to the alpha k squared t f of k. Remember, we multiply both sides by the integrating factor, and that gives us this kind of appearance here, the product rule. So that makes it very easy. Then we integrate this once to release the inside stuff. So we have e to the alpha k squared t capital U equals to the integral of k e to the alpha k squared. I'm going to use a new symbol here, tau now, a tau, because I want to integrate from 0 to t. So when I integrate with respect to tau, I'll just plug in the t at the end. It's like a dummy variable for the time being. Let me take the e onto the other side, u equals to e to the minus alpha k squared t. I can even pull out the f of k, because the integration is for d tau, and integrate from 0 to t of e to the alpha k squared tau, d tau. Let's complete this e to the minus alpha k squared t f of k, and this will be e to the alpha k squared tau over alpha k squared from 0 to t. At the end of the day, it becomes e to the minus alpha k squared t f of k, substitute e to the alpha k squared t minus 1 all upon alpha k squared. So that gives us the Fourier transform u. So suppose it was given that f of x, the function f of x, was x over x squared plus 1. Now we have already worked out earlier on that the Fourier sine transform of x over x squared plus 1, which is actually f of k, is actually e to the minus absolute k. So in this case, we will write capital U as e to the minus alpha k squared t times e to the minus absolute k into e to the alpha k squared t minus 1, sorry, minus 1 like this, minus 1, all upon alpha k squared. And now to get to the final result, we need to integrate this. Small u of xt, small u of xt is given by the integral from 0 to infinity of capital U, which is e to the minus alpha k squared t minus absolute k into e to the alpha k squared t track 1 alpha squared k sine kx dk. So this is the solution. Of course, it doesn't look very interesting because it still has an integral, but the explanation is that you can find this integral by using numerical methods, like Mathematica and so on, can easily handle this here and give you the answer to a certain degree of accuracy. To actually integrate this might be quite difficult. Sometimes it may not be possible to find an actual integral explicitly. Finally, let's take the Laplace equation. How do you handle the Laplace equation? Laplace equation, uxx plus uyy equal to 0. Okay, so we'll have a semi-infinite sheet like this. Let's say the temperature there is 0, temperature there is 0. Let's say the temperature here is some function of x. So we could say your boundary conditions, let's say this is L. So u of xl is 0, u of x 0. So anyway here, any x value is f of x. And on the top here, well, we got u of xl, but on this side here, u of when x is 0 and y is anything, that's also 0. So now let's solve the system subject to these constraints. Solution. Let's call this number 2. Take. Oh, by the way, the reason we are taking the Fourier transform, sine transform in both examples is because we have the Dirichlet conditions in play. So we expect that the sine transform will be the useful one and not the cosine transform. So take the Fourier sine transform on both sides of 2. Both sides of 2. So you get the Fourier transform of uxx sine transform plus the Fourier transform of uyy equals to naught. So uxx is minus k squared capital U, if you recall. This is capital Uyy equals to naught. And we now have a second order differential equation, uyy minus k squared u to naught. Now recall here we have a negative eigenvalue. Negative eigenvalue minus k squared. K squared is a positive thing because it's a perfect square. Minus k squared is definitely known to be negative. Therefore, the suspects are u could be of the shape a cosh something plus b sinh something, right? Because of the negative eigenvalue. But we need the function to vanish or to become 0 at y equals to L. So we make the adjustment of this type here so that we can satisfy this requirement. So we rather choose big U to be, let's see, something like B sinh K into L minus Y. So now when you plug in Y equals to L over here, you'll have L minus L equal to 0. So this will work out quite fine. So this then implies that U, small u, be clear on this, small u is the integral from 0 to infinity b of k sinh k into L minus y sine kx, because we use the Fourier sine transform, dk. And using the condition that u of x naught, when or u of xl, well, u of xl is equal to naught. No, let's use u of x naught equals to naught. We've already used u of xl because that's how we made it in L minus y. So sorry, u of x naught is f of x. That was given by the conditions on the top. We get, when you substitute L to be naught, you get naught to infinity b of k sine k L, because y is naught, yeah? Sine kx k. Fine. So can we write this function f of x in the shape of an integral of that type? So you will recall that we can write f of x in the shape integral of some capital F of k sine kx dk from 0 to infinity, provided that this f of k is actually 2 over pi integral from 0 to infinity of x sine kx dx. So you'll see the structure is exactly the same as what we have above it. So this suggests that b of k sinh kl is exactly the same as this f of k, right? So that means the f of k, or the b of k, will be f of k over sinh kl. Now the f of k will depend on what function f of x is. Okay, so finally you can say that u is equal to the integral from 0 to infinity. B of k is f of k over sinh kl. sinh k of L minus y sine kx dk from 0 to infinity. So suppose f of x was, let's say, the same function, x over x squared plus 1. And we know that f of k in this problem here would be e to the minus absolute k. So we would get the solution u is integral of 0 to infinity e to the minus absolute k over sinh kl sine sinh k into L minus y sine kx k. And this would then be the final solution that we require. Again, it's in the shape of an integral, which means that you might have to use some kind of technique such as numerical integration or the use of some software package like Mathematica to find the specific values of the temperature at each xy value. Remember, this is u of x and y. So by integration, with respect to k, you can find out exactly what the temperature will be at different points xy on this sheet of this semi-infinite sheet that we have at hand.